So by now, we know the laws of physics. And when I say the laws of physics, I mean basically all of the fundamental laws from which all of the rest of physics is derived. We know general relativity, Einstein's theory of curved space-time, which manifests itself as gravity, and we know the standard model of particle physics. We didn't dig down into the quantum mechanical underpinning of the standard model, but the standard model plus general relativity is enough to cover every experiment we've ever done and get the right answer. Nobody believes these are the final answers to the laws of physics, but as far as all the experiments we can do here on Earth are concerned, they are good enough to match the data. The best indication that we have that there's physics beyond the standard model and general relativity comes from the cosmos, comes from dark matter and dark energy, which we're trying to understand in these lectures. So today what we're going to do is take the laws of physics and put them to work in the universe. We're going to take the universe we see, the large universe that is smoothly distributed with galaxies and dark matter and dark energy we'll eventually see. We're going to wind the movie backwards to the very early parts of the universe, plug in the laws of physics, and we're going to make predictions for what we're supposed to see now at the end of all this process. Using the laws of physics and what we know about the early universe, what should we be seeing today? In other words, we're going to be doing paleontology, essentially. We're going to be looking for fossils, but instead of looking them in the ground that are 100 million years old, we're going to be looking for fossils in the sky that are 14 billion years old, leftover particles from the earliest moments of the universe's existence. Partly, this is just because we want to make sure we're on the right track. We think we have a picture that fits the data. We want to use that picture to make predictions and then go test them. But also partly, we want to learn about what can come next. We think that we have excellent evidence that there is dark matter in the universe, for example. The dark matter particles are going to be relics from the very early universe. We need to understand how those particles are created, how the laws of physics can be used to predict how many particles of each kind there are. So we need to understand different features of particles in different circumstances. We need to understand what particles do when they're by themselves, and what particles do when they're in a box with a whole bunch of other particles. Ultimately, the box will be the whole universe. So what we mean when I say what particles do, we mean a particle can either decay or it can be stable. It can sit there forever, not moving, or it can turn into other particles. It can also bump into other particles, and that will be relevant for the early universe when the densities are very high. So let's just think about particles decaying versus particles being stable. Why do some particles last forever and other particles go away? Well, there are rules that govern when one particle can decay into some set of other particles. For our purposes today, there are basically two rules. One is that heavier particles decay into lighter particles. The second rule is that there are conserved quantities. There are numbers that don't change in any process in particle physics, including the decay of one heavy particle into a set of lighter particles. So let's put both of those rules to work in the particle physics that we already know about. The first rule says heavy particles decay into lighter ones. This is basically a consequence of the conservation of energy. We know that mass is one form that energy can take. To a very good understanding, the energy of a particle is the energy that is in its mass, even if it's just sitting there, plus the energy of its motion, plus the kinetic energy of the particle flying through space. Those two forms of energy together tell you what the energy of the particle is. So if we have a heavy particle, and we want to ask what can it decay into, it can certainly not decay into an even heavier particle. There's no way for the energy of the final state to match the energy of the initial state. A light particle decaying into a heavy one would violate conservation of energy. But when a heavy particle decays into lighter particles, it can match conservation of energy even if the masses do not precisely align. Since there's only a finite number of particles, it would be very surprising, in fact, if the masses of the first particle were exactly the sum of the masses of the second particles. What happens is the extra energy is taken up in the kinetic energy of the outgoing particles flying away. So, for example, a classic example of an allowed decay of a heavy particle into lighter ones is the decay of the neutron into a proton, an electron, and an antineutrino. We see that happen in nature. The lifetime of the neutron is something like 10 minutes. So it must be the case that the mass of the neutron, the energy that the neutron has from E equals mc squared, is greater than the sums of the masses of the proton, the electron, and the neutrino. The neutrino is very, very light, so it almost doesn't play a role in this. But when we look at the numbers, The neutron rather, and the proton are both much heavier than the electron. The neutron is a little bit heavier than the proton. In units of masses of the electron, the neutron is 1,879 times as heavy as the electron. The proton is 1,877 times heavier than the electron. So the neutron, 1879 electron masses, decays into the proton, 1877, plus the electron, which is 1. You get a sum which is 1878, still less than the 1879 that is the neutron. So that's why it's allowed to go. The fact that these numbers are so close, the fact that the masses of the proton plus electron plus neutrino is almost equal to the mass of the neutron, is one of the reasons why the neutron is so long-lived. There's not a lot of possible arrangements for the outgoing particles. Now consider the possibility of the proton decaying. What could the proton decay into? Well, when you think about it, you might want the proton to decay into a neutron, a positron, and a neutrino. That would conserve electric charge because the neutron and the neutrino are neutral. The positron has a positive charge just like the proton. But this event never happens. Protons do not decay into a neutron plus a positron plus an electron neutrino because it doesn't match energy conservation. The proton is lighter than the neutron and therefore it will never decay. It's interesting to speculate that the universe would be a very different place if the masses of the elementary particles were a little bit different. What if the mass of the proton were a little bit larger than the mass of the neutron? Then it would be the other way around. The neutron would be stable. There would be nothing for the neutron to decay into. But the proton could decay. The proton would decay into a neutron, spitting off a positron. What do all those positrons do? They go around and they annihilate with all the electrons. In other words, we'd be left in a world with nothing but neutrons and neutrinos if the proton were heavier than the neutron. That would be a very, very different world than in the one in which we live. There'd be no atoms, there'd be no chemistry, no molecules, anything like that. So we're very lucky that the mass of the proton is a tiny bit less than the mass of the neutron. The second rule relevant to what can happen in particle physics is that conserved quantities don't change. That's what the word conserved means. The most obvious example of a conserved quantity is, of course, electric charge. It's sort of intuitively obvious to us that the electric charge shouldn't change in particle physics reactions. So, for example, the electron, for historical reasons, has a charge -1. The proton has a charge +1. That's because it's made of 3 quarks. The 2 up quarks in the proton each have a charge of +2/3 each, and the 1 down quark has a charge of -1/3. So it adds up to +1. The neutron is electrically neutral, just as the neutrino is. The neutron comes from 2 down quarks, -1/3 each, and 1 up quark +2/3, so they add to 0. So in any process that can happen, the electrical charge of all the particles at the beginning must equal the sum of the electrical charges of all the particles at the end. So for example, a neutron cannot decay into a proton, an electron, and a positron. That would be allowed by energy conservation, but you would have a total charge of +1 at the end. You had a total charge of 0 at the beginning. So that is not allowed. No one would even have guessed that that should be allowed. We sort of understand immediately that electric charge is not created or destroyed. But it's a good paradigm. It's a good example of something that happens, something that doesn't go away, and we have more subtle examples before us that play a big role in particle physics. The 2 other examples I want to mention of conserved quantities, of numbers that don't change in particle physics interactions, are quark number and lepton number. Basically, the quark number is the total number of quarks. The lepton number is the total number of leptons. The only subtlety there is that when we say the total number, antiparticles count as negative. So the difference between a particle and an antiparticle is that all of the conserved quantities for the particle are the opposite of the value of those conserved quantities for the antiparticle. So you know that the electron has charge -1, the positron has electric charge +1. They're opposites. Similarly, the lepton number of the electron is +1, so the lepton number of the positron must be -1. The total amount of conserved charge for a particle and its antiparticle will always add to 0, so they will always be opposites. Quarks have quark number +1 and lepton number 0. There's no lepton number associated with quarks, just as there is no quark number associated with leptons. So then you add them up inside a proton or a neutron, and you get a total quark number of 3. There are 3 quarks inside a proton, therefore the quark number is 3, likewise for a neutron. Remember that we defined different ways that quarks can get together to form heavier particles. We called a baryon any collection of 3 quarks. All the 3 different colors combined to give you one white baryon. So sometimes people talk about baryon number, which is exactly equivalent to quark number divided by 3. So the baryon number of the proton is 1 because it has a quark number of 3. Now consider the pion, for example. The pion is a meson. It's made of 1 quark and 1 antiquark. So if you think about it, the quark number for a pion is 0, or likewise the baryon number for a pion is 0. Even though it's made of quarks, 1 quark and 1 antiquark, the total quark number of the pion is 0. You can make as many pions as you want, you're not changing the quark number. So the way to think about this is almost as if there's some stuff, almost as if there's some substance that changes its form, rearranges how it appears, but it is never created or destroyed. Some nugget of quarkiness that can change from being an up quark to a down quark, or vice versa, as neutrons and protons intercommute, but it never disappears. It never goes from being a quark to being an electron or something like that. So all of the reactions that we can possibly have in the universe will keep the quark number the same, and it will keep the lepton number the same. Here's an example. You might think, if you were only thinking about electric charge, that the proton could decay. The proton could decay into a positron, an anti-electron, and a neutrino. That would keep the electric charge constant. You would have electric charge plus 1 for the proton. It would turn into electric charge plus 1 for the positron, plus the neutral neutrino. The reason why protons don't decay in the real world is because quark number is conserved. So again, this is a happy feature of the world in which we live. If quark number were not conserved, the protons would all dissolve into positrons. Those positrons would annihilate. You'd be left in a universe with nothing but neutrinos and photons. Again, not a very exciting place. Likewise, lepton number tells you certain things can't happen. Imagine a neutron trying to decay into a proton plus an electron. This is what people used to think neutrons actually did. They saw the neutron sit there and they saw the proton and the electron come out. The total electric charge is 0 before and after. The total baryon number is 1 before and after. It was 1 neutron with 3 quarks turning into 1 proton with 3 quarks plus an electron. However, we now know that that can't happen. The reason why it can't happen is because it violates lepton number. There were no leptons before, and then there's an electron lying there afterward. That's why when a neutron decays, there must be an antineutrino involved. That antineutrino carries lepton number minus 1. So the total lepton number at the end of the day, with the proton, the electron, plus the antineutrino, adds to 0. So the neutron is allowed to decay if there's that antineutrino there. It wouldn't have been able to decay if there weren't. Now, when we talk about historically, how do you invent these conservation laws? How do you figure out what is conserved and what is not? You don't do it by saying, aha, I think some numbers should be conserved, let me go look at the interactions. Usually what you do is you do particle physics, you measure what interactions actually do happen, which interactions happen quickly, which interactions happen slowly, and then you try to figure out why certain things don't happen. That's how people come across things like the conservation of quark number or the conservation of baryon number. People knew that baryon number was conserved long before they knew what a quark was. They could see that neutrons didn't decay into neutrinos or something like that. There must be some conserved quantity there. That's how the game is usually played. Having said that, we should admit that some rules are more solid than some other rules. Electric charge really is conserved. It is true that quark number and lepton number have never been seen to be violated in any experiment that we've ever done, but we wouldn't be that surprised if someday we found that they were. In fact, there are theories in which they are. It's just very, very slow that it happens, and we haven't seen it yet. Electric charge is something that we really don't think is violated. If someone claimed to do an experiment and they found that electric charge was created or destroyed, basically nobody would believe them unless they had some cachet for other reasons. It's something that no one expects on any theoretical basis. You can notice, for example, that when you look at the whole universe and add up its electric charge, you get a number that is zero, as far as we can tell. There are an equal number of electrons and protons in the universe. The universe is electrically neutral. That is not true for quark number. It might not even be true for lepton number. The truth is we don't know, because we don't know how many neutrinos are out there. Neutrinos versus antineutrinos contribute to the lepton number, and we can't count them. But we can count the quarks. The quarks show up in protons and neutrons. We can count them. There are many, many more quarks in the universe than there are antiquarks. It could be that that's just how the universe started. The quark number is truly conserved, and there's been this imbalance all along. But honestly, nobody believes that. What everyone really believes is that in the very, very early universe, the quark number was zero, and there was some dynamical process that really did violate quark number and created that imbalance. That whole game that we try to play, creating quark number where there wasn't any before, is called baryogenesis, creating baryon number out of zero baryon number. We don't understand baryogenesis very well. It's an open research project that we would like to understand better. Part of the ways that we're trying to understand it better is actually to do experiments here on Earth that would witness baryon number being violated. There are proton decay experiments, which conceptually are the simplest things in the world. You get a big vat of stuff that is not radioactive, stuff that doesn't emit any form of high-energy particles. You put it deep underground where no one will bother it, where no cosmic rays can come in and bump into it, and you wait for something to happen. What you're waiting for is for a proton to turn into, for example, a positron plus a neutrino. That keeps electric charge okay, it keeps lepton number okay, but it violates quark number. We've never seen it happen, but we're looking. As soon as we do see it happen, that'll be a great advance towards our understanding of the laws of physics. Okay, so those rules are telling us what happens to a particle sitting all by itself. What particles can decay into others, which ones are stable. Many of the particles that we've talked about so far are stable. The neutrino is stable, the electron is stable, the proton is stable. Why? If you think of it, you can't tell me any set of particles that those guys can decay into while both being less massive and keeping all the conserved quantities conserved. The proton is the lightest particle that carries baryon number, that carries quark number. Therefore, it can't go into anything else. The neutrino is the lightest particle that carries lepton number. The electron is the lightest particle that carries electric charge. So that's telling us why these particles can't decay. They have nowhere to go. The dark matter is another particle which seems to be stable. One nice way to make new theories of dark matter is to invent new conserved quantities that explain why the dark matter particle has lasted for the 14 billion years that the universe has been around. Now let's take some of that understanding and put it together in the early universe, where you don't just have one particle sitting there and decaying, you have a bunch of particles. So the early universe is compact, things are squeezed together, the density is very high, and this means two things. One thing it means is that interactions happen very frequently. Particles are right next to each other, they keep bumping into each other. The second thing it means is that because the temperature is high, the energy per particle is very high. That's basically the definition of temperature. It's the average energy per particle. So if the energy of a particle is its rest energy, its mass, plus its kinetic energy, when the energy is very, very high, the particles are all moving very, very quickly. And what that means is that new things can happen. Consider an interaction where a proton bumps into an electron. Now, that interaction already happens all the time in a hydrogen atom. That's what a hydrogen atom is. It's an electron spinning around a single proton. And you can ask, what happens? The answer is nothing. The hydrogen atom can sit there forever. But if we go to the early universe, when the temperature was very high, instead of just the electron sitting there on top of the proton, we have an electron and proton running into each other with a large amount of energy. What can happen then is they can collide and turn into a neutron plus an electron neutrino. The total charge of that interaction goes from a total of 0 to a total of 0. The total quark number goes from being 3 to being 3. The total lepton number goes from being 1 to being 1. Everything is conserved. The only thing you're trying to do is to add energy to the system so you can turn lighter particles, a proton and an electron, into a heavier combination. You can do that conserving energy if you're at high temperatures. So that's the kind of thing that becomes possible in the early universe when all the particles are zooming around very rapidly, bumping into each other. So this gives us a way of asking what can happen when you go from the very early universe, when things are hot, dense, bumping into each other, to the very late universe that we see today. Today in the universe, things are very, very dilute, things are not bumping into each other all the time, and things are very cold. The universe right now, technically speaking, is not in what we call thermal equilibrium. I am not at the same temperature as the sun or the cosmic background radiation. But roughly speaking, when we talk about the temperature of the universe, the thing that we refer to is the temperature of that cosmic microwave background. That is the relic leftover stuff from the plasma that used to be in thermal equilibrium. In the early universe, those photons that we now see as the microwave background were rapidly bumping into everything else, and their evolution in temperature is what sets the scale for how hot the universe is. And the way it works is very simple. As the scale factor goes down in the early universe, as things squeeze together, the temperature goes up. And it goes exactly inversely. So when the temperature was twice as high, the scale factor was only half its current size. In particular, when the scale factor was 1/1000th its current size, the temperature was 1,000 times as high, and that's when the microwave background itself was formed. If we keep going back and back and back until when the universe was very, very hot, then we can create new particles that aren't lying around today. Remember, the temperature is the rest energy plus the kinetic energy. It's the average total energy of the particles. So by increasing that temperature, by increasing the total energy, we have enough energy to create heavier particles than we find in the universe today. Whether or not they're stable, they will come into existence. For example, an electron and a positron can come together and annihilate, and you can say, what can they annihilate into? The answer is they can annihilate into any pair of particles and antiparticles, because the total of all conserved quantities for an electron plus a positron is 0. The total amount of conserved quantity in any particle-antiparticle pair always adds to 0, so any particle-antiparticle pair can always convert into any other particle-antiparticle pair. So let's imagine we invent a new kind of particle, call it particle X. And it is a fermion. It comes with its antiparticle, the anti-X particle. The X particle is heavy. We don't make it in the laboratory today. But in the early universe, when the energies were very high, electrons and positrons kept bumping into each other and creating X particles and anti-X particles. What we want to know is, how does the abundance, how does the density of those X particles and anti-X particles change as the universe expands? So there are two events in the thermal history, in the lifespan of this X particle and its antiparticle, the anti-X particle. One is that it becomes cold. So if you think about it, the temperature tells you the average energy of a particle. The energy is the rest mass plus the kinetic energy. And there's two different regimes that you can think about. One in which the rest energy is much larger than the kinetic energy. The other one in which the rest energy is much smaller. If the rest energy is larger than the kinetic energy, that translates directly into the statement that the particles are moving slowly compared to the speed of light. They're more or less at rest, relativistically speaking. We call such particles cold. They're moving slowly. The temperature of the surrounding gas is small compared to the mass of that particle. In the other limit, when the temperature is very, very high, the particle's energy is dominated by its kinetic energy. That means it's moving close to the speed of light, and we call such particles hot. So, of course, as the universe cools down, the temperature of every particle goes down, and there will be a moment in its life when it goes from being hot to being cold. That's the moment when the temperature, the average energy, is approximately equal to the mass of these particles. That's one important event. The other important event is when particles freeze out. That's when particles stop interacting with the particles around them. Now, in the early universe, not only is everything high temperature and high energy, it's also densely packed. Things are close together. So things keep bumping into each other. And things can, for example, annihilate. If you have a positron, it will bump into an electron and annihilate. Today, however, particles are more spread apart. Imagine that you have a positron here in this room, and you're in a strange situation where the nearest positron, which is an electron, is a mile away. It's true that an electron and a positron will come together and annihilate, but if they're a mile away, they don't even know that each other exist. They can't find each other to annihilate. So when things freeze out, when things become so dilute that they don't find each other, they can exist even though there are both particles and antiparticles lying around. These particles and antiparticles could, in principle, annihilate, but they can't find each other. They're left over as a relic abundance. It sounds unlikely for positrons and electrons because they find each other very easily, but then when you talk about neutrinos, or other particles that interact very weakly, they need to be very, very close together to interact a lot. Neutrinos can freeze out very easily. They just interact so weakly, they stop finding antineutrinos and annihilating. That's the general picture. And the two different regimes, hot and cold, can happen at different times with respect to the event of freeze-out. In other words, particles freeze out when they stop interacting. That's one event. The other event is particles go from being hot to being cold. And there's two different possibilities. You first go from being hot to being cold and then you freeze out. You freeze out while you are cold and you are called a cold relic particle. Or you freeze out while you're hot. The only difference in these two different cases is how many particles you're left with. If you're hot, if you're moving very close to the speed of light, your mass is very tiny compared to the energy that is going around. It's easy to make you. It's easy to make light relativistic particles. They don't weigh that much. They will be very, very abundant. When you're cold, however, that means that you're heavy, you're massive, you're lumbering. It's hard to make X particles and anti-X particles if they're cold. Therefore, if a relic is cold, when it freezes out, there will be many fewer of them left around. Now, the obvious application to this kind of analysis is dark matter. You're going to say, we think that there's a lot of dark matter in the universe. It's not a particle that we see very easily. Could it be a leftover from some freeze-out process in the early universe? And this is where you start examining in detail the possibility that neutrinos could be the dark matter. Neutrinos are the only particle in the Standard Model that stand any chance of being the dark matter. They're neutral, and they're weakly interacting. So what happens to them in the early universe? When do they freeze out? The answer is neutrinos freeze out when they're hot. They're very, very light particles, so they're almost always hot. They're almost always moving close to the speed of light. So when they freeze out, they're hot. There's a lot of them. We can calculate very, very accurately the number of neutrinos per cubic centimeter in the early universe and extrapolate it with great confidence to the number of neutrinos in the current universe. They could be the dark matter if they have a certain mass. We know very well what the mass of the neutrino would have to be to account for the dark matter. But we don't think that that's right. We don't think that the neutrinos really are the dark matter. Why is that? Because while they're freezing out, they're hot, they're moving close to the speed of light, and therefore they don't clump together. The characteristic feature that makes us find dark matter in the current universe is that dark matter falls into galaxies and clusters of galaxies. We can measure the rotation curves of galaxies, and we find that most of the mass of the galaxy is dark matter. We can measure the speeds of galaxies within clusters, or use gravitational lensing to find that most of the mass in a cluster of galaxies is dark matter. But if the dark matter was hot, if the dark matter was moving rapidly when it was created in the early universe, instead of falling together under its mutual gravitational field, it would zip around and smooth everything out. The feature that you get when the dark matter is hot is that structure doesn't grow in the universe. The dark matter particles are moving very, very quickly, and instead of falling together and becoming lumpy, increasing the contrast knob of the universe, the neutrinos or other relic hot dark matter particles would simply smooth everything out. This is not a close call either. The possibility that the dark matter is hot has been absolutely ruled out by what we know about the existence of galaxies and so forth in the universe. That's why when we talk about the dark matter particle, we talk about cold dark matter. We talk about a particle that was massive when it froze out, that was heavy, that was moving slowly compared to the speed of light. So what you want is a particle that is heavy and a particle that has enough leftover relic abundance to be the dark matter. If the particle interacted very strongly, there wouldn't be enough of it left over. It would just go away. If the particle interacts weakly, you can make enough of it to be the dark matter. So that is why the leading candidate for dark matter is called the WIMP, the weakly interacting massive particle. If it's weakly interacting, even though there are new particles x and antiparticles x bar, the x particles and anti-x particles don't annihilate away because they just don't find each other. That is the leading scenario for what the dark matter could be. A cold dark matter particle, moving slowly because it's heavy, weakly interacting, and therefore called a WIMP. That's a very general kind of scheme for what could be going on. In the upcoming lectures, we're going to look at specific examples for things that can be left over from the early universe. We'll look at specific examples of WIMPs, to be sure, for the dark matter, but also more mundane examples like helium, something that we've actually detected, and even better than that, the cosmic microwave background, all of which things are going to give us great clues to what the universe was like at very early times.